Hello everyone, I'm Shashwat from Team 7. Our project is titled Bridging NDT Inspection and Reliability Testing in IC Packaging. The core idea, as written on this slide, is that we identified the research gap between two parallel communities, NDT inspection, covered by Aryan and all, and reliability testing, covered by Bender and all, and then bridge it through three Python simulations that translate NDT signals directly into physics of live failure prediction. I'll introduce the background, my teammate will take you through the gap, the bridging literature, and all three simulations. The core engineering problem is right here in the title. There is a fundamental mismatch between how small IC packaging has become and how fine our NDT inspection methods can resolve. As packaging has evolved from DIP in the 1960s with relatively simple defects like lifted lids through PGA, BGA, flip chip, and now into 3D heterogeneous integration, the structural features have shrunk dramatically. As Bender et al. 2024 notes, feature sizes will soon reach the order of a few nanometers, and the defects that matter still have become correspondingly complex: delaminations in underfill, crack and micro bumps, voids inside through silicon wires. The problem is clear when you look at the NDT resolution gap box at the bottom, which comes directly from figure 3 of Aryan 2018. Current NDT voxel sizes range from 1 to 10 micrometers for X-ray, down to 100 micrometers for SAM, completely inadequate for submicron TSV defects. The gap is most severe for SAM and SAW, which are also the most widely used inspection tools in production today. That is not an academic concern, it is a crisis. Aryan and al. In 2018 reviews 6 major NDT methods, all shown here. I want to go through each with both what it does well and its critical limitation. X-ray and CT. Its resolution is 1 to 10 micrometers. It penetrates the substrate, detects voids, cracks, and delaminations, and is already used in automated production lines. The limitation, however, is that full CT takes hours and submicron resolution is physically unachievable. Scanning acoustic microscopy, SAM. It detects delamination, voids as small as 125 micrometers, and solder bridging. It has 3 scan modes and no radiation hazard, but it requires a deionized water coupling medium, suffers from edge defects, and faces a resolution versus penetration depth trade-off. To see smaller defects, you need gigahertz frequencies, but penetration drops severely at those frequencies. SAW. Surface acoustic waves, mostly non-contact, using laser excitation and Doppler sensing. It is sensitive to cracks over 15 micrometers with no couplant needed. However, it cannot access underfill or bumps with pitch under 100 micrometers and requires a reference baseline. Infrared thermography. It's non-contact, it detects missing bumps, delaminations, silicon cracks, and even works on 3D packages in lock-in mode. It has the best spatial resolution. It has a spatial resolution of 3.75 micrometers. However, its limitation is that it's limited to surface or near surface because penetration depth equals the infrared wavelength. At submicron scales, the temperature contrast is simply too small to detect. MCI maps hidden current paths. It's excellent for short circuit localization and achieves micron resolution, but it only works on conductive materials and requires a defect-free reference sample. Ultra-fast laser. Submicron resolution using gigahertz to terahertz acoustic pulses. It is non-contact and has reasonable scan time, but it is complex to set up and largely unvalidated for the production IC packaging. The key sentence is at the bottom of the slide, which sets up everything that follows. None of these methods automatically translate their defect signal into a physics of failure reliability prediction. That is the gap my teammate will now explain.
Hi, my name is Ashok Naik and I'll cover what Bender 2024 establishes about reliability testing and then present the research gap that is the foundation of this project. So Bender's framework is the physics of failure pyramid on the left. The core argument is that you can't just run a stress test and call a device reliable. You must start at the base, identify physical vulnerabilities of every material, encapsulate them into a mathematical model, and then formulate a multi-dimensional mechanism model, then carefully design multi-stress test cases, and only then you get a meaningful reliability prediction profile. So the table on the right shows the 5 dominant failure mechanisms. The first one is solder joint fatigue, the most common BGA failure. It is normally modeled by Coffin, Manson, and Norris-Landsberg extension, accelerated by temperature cycling between -65 and plus 150 degrees Celsius. The second most dominant failure mechanism is electromigration, which mainly takes place in high current interconnects, which follows Black's equation. Empirically, N is normally taken to be 1.8 and activation energy around 0.8 electron volts. Corrosion is also another important failure mechanism where from moisture, which uses Peck's model and is accelerated by Haas test at 130 degrees Celsius and 85% relative humidity. Finally, delamination cracks, which involves CT mismatch modeled by Miner's rule and FEA plastic strain. Wire bond fracture is also another mechanism that is characterized by IMC growth and viable heel crack distributions. The important thing is given at the footnote, which tells us that the standard JEDC qualification tests are pass-fail with a single acceleration factor. They cannot isolate multiple coexisting failure mechanisms to predict remaining useful life. That limitation, combined with what was just described, produces the gap. Yeah. So this slide is the most important slide in the deck. So I will be spending some time on it. At the top, you can see two boxes that define the gap cleanly. On the left, you have the paper from Aryan 2018 detects defects through X-ray, SAM, IRT, MCI, and ultrafast laser. The approach is one shot or pre-post screening only. It stops at detection and there is no life prediction. On the right, the paper given by Bennett 2024 performs accelerated stress tests and applies physics of failure models. But critically, the damage inputs in those models come only from destructive cross-section analysis of FEA simulation. And the gap label in the middle is the precise problems the project is trying to address. So, the statement in bold below both the boxes defines our contribution, which is NDT data to physics failure model reliability prediction, which is the frontier research explored from 2019 to 2025. Now, I will go through some important research papers that were explored during this duration. So the first paper explores 3D X-ray images of microbumps in a 3D IC, fed them to a convolution neural network and predicted bump failure by identifying area loss at the bump midplane. This is NDT data directly determining reliability with no destructive testing. The second paper talks about a linear correlation between X-ray CT void fraction and Coffin-Manson fatigue for BGA in live solder balls. This paper directly calibrates the parameters we use in simulation 3. Now, the next paper talks about SAM A-scan signals alone processed with machine learning, classify flip chip bumps as intact or defective. No cross-sectional analysis is needed. Now, the next paper talks about IE transactions, RAN laser ultrasonic measurements through an actual thermal cycling reliability test on industrial SC BGA packages. So this is NDT inside an accelerated stress test, exactly what neither anchor papers implements. And lastly, the 2024 IIT plus MLP paper looks at couples lock-in IIT phase images with neural networks to quantify delamination depth and area. The physics chain are simulation to implement scientific. Now, for this particular slide, so I'll walk you through simulation 1 and 2 briefly that we implemented for this project. So both simulations take a specific NDT signal and trace it all the way to reliability prediction. That's the bridge we've been describing. Simulation 1 mimics exactly what scanning acoustic microscope would measure. The physical setup is a 200 by 200 micrometer FDTD domain at 1 micrometer per cell. Three layers copper pad at the top, SAC 305 solder in the middle, and 30 micrometer air void at the ball center. We inject a 50 megahertz Gaussian modulated pulse, the standard SAM transducer frequency range. What we measure is an A-scan records the back scattered pressure over 3000 time steps, and the Hilbert envelope, which extracts the echo amplitude, and a B-scan produced by rastering 20 source positions across Y, stacking each A-scan column to reveal void position in 2D. Now, the reliability bridge on the right, we run this for void diameters from 0 to 120 micrometers, extract the echo amplitude at each size, and map it to Coffin-Manson fatigue life using NF equals 3000 cycle times times 1 minus 1.8 times the void fraction void area fraction. So the threshold corresponds to 80 micrometers for our 160 micrometer ball, and the bottom box in the end shows the connection explicit shown by the paper from R in 2018, which shows Sam can detect voids but gives no live prediction. Bender uses Coffin Manson but relies on destructive cross sectioning for void. This simulation provides the continuous NDT signal to live curve the exact connection both papers. Now, for simulation, sorry. On the left is the material map. Yellow is the copper pads. Orange is SAC 305 solder, and the dark circles is the 60 micrometer void. The color is the speed of sound. The color axis is the speed of sound. Copper is 4,660 meter per second. Solder at 3,330 and air void at 343, which is the standard what we expect. The tenfold difference in acoustic velocity is the void, is why the void creates such a strong reflection. The acoustic impedance mismatch is large in this case. On the right, we have six times snapshots of pressure fields as the wave propagates. Note three things from the key observation box. The void has 10 times lower acoustic velocity than solder, creating a large reflection. The second point mentioned the 50 megahertz pulse has a wavelength of about 66 micrometers in solder, which is why it can resolve a 60 micrometer void. The wavelength is comparable to the defect size. And lastly, the more absorbing boundary conditions are applied at all edges to prevent spurious reflections from grid boundary. Lastly, at t equals 29 nanoseconds, you can clearly see the wave diffracting around the void boundary. By 33 nanoseconds, scattered field is returning back towards the source. This energy is the A scan echo. Now, the remaining PPT will be taken up by my team. Thank you.
Hi, I'm Dhriti Mandar, and I'll continue with the simulations. That is the simulation of the SAM acoustic wave propagation and its results. The top plot is the A scan. Blue in this graph is the pressure signal, red is the Hilbert envelope, and the gold dashed line marks the void echo arriving at 80.1 nanoseconds. To verify this physically, 80.1 nanoseconds multiplied by 3300 meters per second divided by 2 round trip gives 132 micrometers of travel. Our void is at 100 micrometers from the top copper surface. So the signal has to travel through 20 micrometers of copper, 80 micrometers of solder, bounce off the void and return. The numbers are consistent. Below is the B scan, a hot color map of envelope amplitude. X-axis is the lateral scan position across the 20 source locations, whereas the Y-axis is the time in nanoseconds. The bright horizontal band appearing around 75 to 85 nanoseconds consistently across all scan positions confirms the void is uniformly present beneath the surface, exactly as expected for a centered spherical void. The key bridge point in the interpretation panel is that the peak echo amplitude from the A scan increases with void diameter. The Hilbert envelope maximum directly encodes the void size, then void fraction, then the Coffin-Manson NF. One SAM measurement equals 1 point on the reliability curve. The next slide shows this calibration. This is the current output of simulation 1. The blue curve is SAM echo amplitude versus void diameter. It rises monotonically because a larger void creates a larger acoustic impedance mismatch area, scattering more energy back. The red dashed curve is the predicted Coffin-Manson fatigue life on the right axis. It falls linearly from 3000 cycles at 0 void down to 0 as the void fraction approaches 36%. The gold dotted vertical line is the IPC 7095D, 25% void area threshold at 80 micrometers. Reading this plot as an engineer, if you measure a SAM echo amplitude somewhere on the blue curve, you immediately read off the void diameter from the x-axis. Then you move vertically to the red curve and read off the predicted remaining thermal cycling line. Any void beyond the gold line predicts fewer than 1500 cycles to failure. As the key takeaway box confirms on the right, any SAM measurement can now be translated directly to a remaining useful life estimate. This is exactly the bridge missing between the two papers, RE and Benders, and it is demonstrated with a 200 micrometer FDTT simulation. Coming to the simulation 2 of the lock-in infrared thermography. Simulation 2 applies the same bridging philosophy to this technique. We model a flip chip cross section as a 30 by 20 grid with 200 micrometer cell size, a 6 by 4 millimeter domain. The layer stack is silicon die at the top with thermal conductivity of 130 watts per meter Kelvin, solder bumps alternating with air gaps at K equals 50 and 0.026, PCB substrate at K equals 0.3, and the delamination of one cell air gap at row 7 with K of 0.026. We apply a sinusoidal surface heat flux that matches lock-in IRT excitation. The lock-in demodulation is surface temperature is sampled over 4 cycles. The last 3 are demodulated to extract in-phase and quadrature components, giving amplitude and phase. The delamination appears as a phase anomaly because air blocks heat flow towards the substrate. The reliability bridge on the right, and this is the 3-step chain. Delamination width detected from the phase anomaly gives us the delamination area. Thermal resistance del Rh equals the delamination thickness divided by K times area. Junction temperature rise is power times thermal resistance with 5 watts of dry power. That delta Tj feeds the Arrhenius acceleration factor with activation energy of 0.7 eV and nominal use temperature 358 Kelvin. Remaining useful life and percent equals 1 over AF times 1000. The bottom box closes the gap. This simulation provides the full chain from IRT phase image to RUL that closes both gaps simultaneously. Going through the results of the simulation. On the left is the material map of the flip chip cross section. The color scale is log base 10 of thermal conductivity. Silicon at the top is the brightest, K equals 130. The PCB substrate at the bottom is the darkest purple, K equals 0.3. That is 4 orders of magnitude difference, which means the thermal pathway through the package is dominated by interfaces, not the bulk material. The black columns in the solder bump layer are the air gaps between bumps. These already create a thermal barrier. The lime green rectangle, that is our delamination. It is a 200 micrometer thick air layer inserted at the die substrate interface at around 1.5 millimeters depth. That's what the IRT simulation must detect. On the top right is the critical frequency selection plot. The thermal diffusion length, how deep a lock-in thermal wave can probe, equals the square root of thermal diffusivity divided by pi times frequency. We need this length to equal our delamination depth of 1.4 millimeters. That gives an optimal lock-in frequency of about 0.5 Hz, shown by the gold dotted line. The surface temperature plots at bottom right confirm the signal is already visibly different with and without the delamination, even before demodulation. On the left are the lock-in demodulation results. The top panel is the phase image. The red line is with the delamination, and the blue dashed is without. Inside the delamination zone, that is the green shaded region, the phase with delamination rises distinctly above the flat baseline. That is the IRT signature. The air gap blocks the heat flow, creating a local phase anomaly directly over the defect. The amplitude image below confirms the same effect. On the right is the 3-panel reliability bridge. Plot 1. Even a 0.5 millimeter delamination raises junction temperature by about 120 Kelvin. This is because the air conducts heat poorly and the block pathway forces thermal energy to accumulate at the die. Plot 2. The Arrhenius acceleration factor rises exponentially with delta Tj. A 100 Kelvin rise gives AF greater than 10 to the power 5. The device reaches end of life at around 1 lakh times faster than at its nominal operating temperature. Plot 3 is the remaining useful life drops to near zero for delamination widths above about 0.2 millimeters. The 50% threshold, that is the gold line, is crossed almost immediately. The bottom note on this on the slide uh, says this clearly. This shows why even small delaminations detected by IRT are critical reliability events and not just cosmetic issues. IRT detects, our simulation converts that detection into a quantitative, actionable RUL estimate. Thank you.
Hi everyone, I'm Archit and I'll be explaining the third simulation. The simulation is based on an X-ray approach which does statistical population study, and rather than predicting a single life of a single defect, we generate 500 samples representing 500 solder balls from a production batch, each with different random void configuration. And we try to ask what is the Weibull life distribution of this sample. The void extraction is done by thresholding, and then we predict the void fraction in the sample. Then we use the Coffin-Manson approach to find the reliability of all the 500 samples. Any sample above 25% void fraction have been classified as rejected. The Weibull fit gives beta with approximately 1.07, which means near exponential growth, meaning random void placement dominates. And the eta value is 1385 cycles, and mean life equals 169 cycles. As the bottom box states, previous literature studies have used X-ray to quantify voids and also lead to Weibull life predictions. So this non-destructive method is quite applicable for BGA solder joints. Moving ahead, we have synthetic X-ray images at void fraction versus fatigue life graphs. On the left, there are 12 representative images sorted by void fraction. On the upper left, you can see green samples, which mean that they have passed the test. And on the bottom right, you can see the rejected samples. And one thing to notice is that it is not easy for the naked eye to tell which samples have to be rejected or which samples have to be passed. Certain samples on the top left can directly mean that, oh, the void is very small. But as we get towards the center, the criteria becomes very difficult to implement. So that is what our model demonstrates. On the right side, we have a scatter plot of all the 500 samples with void fraction on the x-axis and predicted NF on the y-axis. The gold vertical line is the IPC 25% threshold. Everything on the right is rejected. The key observation is that samples just left of the threshold still show low predicted lives because they contain one large dominant void, even though total void fraction is under 25%, which motivates the Dmax plot, which we will explain on the next slide. Moving ahead, on the next slide, on the top left, we have the Weibull probability plot. The blue dots are the 500 Monte Carlo samples on the Weibull linearized axis, which are log in 1 by f, and on the other axis, we have log of nf. The red line is the two-parameter Weibull fit, which is beta of approximately 1.07, as mentioned before. The distribution is again approximately exponential. On the top right, largest void diameter Dmax versus predicted NF dot has been shown. The blue points tell the blue points are the points that have passed the IPC test, and the red points are the points that have failed the IPC test. Large voids, even a single one, push NF forward to zero, regardless of total void fraction. This confirms that Dmax is a necessary complementary inspection metric. Three histograms at the bottom summarize the data set, where void fraction is roughly uniformly distributed from 0 to 50%, and the predicted life is heavily skewed. Mostly balls clustered near a 3000 cycle baseline, but the tail extends to very short lives. And finally, to conclude our project, let's bring everything together. On the left is what we showed in the project using the three simulations, with the first simulation being a SAM echo amplitude, and we tried to find that one SAM measurement can equal one reliability data point. In the second simulation, we have lock-in IRT phase anomaly revealing delamination area. And like we recently discussed, in the third simulation, we have X-rays to detect void fraction and then in turn, which predicts the reliability life of a sample. And recent literature by Sun in 2022, by Wang in 2023, and by Chen and Uma in 2021 have supported our approaches towards these simulations in the way that we have done them. On the right are some future directions that one can follow. Uh, One being, of course, ML and AI integration, as with everything these days. advanced packaging. Improvements in packaging can enable NDT, easier NDT measurements that give real data. Digital twins can also help streamline process, help with earlier predictions of failures in the models. And so to conclude, we have tried to simulate certain energy methods and also provide future directions that can be used to progress and help better sampling characterization of advanced packages. Thank you.